For this lab, I observed two objects being dropped. One object, a cat toy, fell fast, and the other, a Christmas ribbon, fell slowly due to the force of drag. I then created models for both cases with and without drag. The results of this lab were that drag was almost negligible for the fast-moving object and approached the gravitational force on the slow-moving object. Here is my fast-moving object. I recorded the drop from a velocity of 0 at an initial position of 2.022 meters above the origin, which I chose to be my brother's foot. The video is calibrated to the height of my brother, 1.82 meters, and lasts for 0.533 seconds. This was tracked and my data recorded. The slow-moving object is shown here, and the same method was used to record the data. This video lasts for 0.7 seconds. I made a computational model with and without drag. Without drag, I adjusted the timescale and object mass to fit the observations. My time step is 0.01, which is appropriate for this system. I used Newton's second law to update the velocity and position equations. To update velocity, I used initial velocity plus net force over the mass of the object times delta t, and to update position, I used initial position plus velocity times delta t. Without the effects of drag, F net equaled the force of gravity. The net force is different in this model for drag. The net force with viscous drag is the force of gravity plus the drag force, which is given here. The constant B is found experimentally. Notice the blue arrows represent the force of drag against the force of gravity. The observed data was then graphed with the model data, observed being the dark diamonds. Here are the comparisons for both objects with zero drag models. As you can see, the fast-falling object fit the drag model much more closely than did the slow-falling one, meaning that drag had a significant effect on the slow-falling object. When the models were corrected with drag and B values found experimentally, the model fits the observed data very well, meaning that my drag model is indicative of real-life observation of falling objects. The drag force was much larger in the ribbon with a multiplier constant of 0.009 compared to the multiplier constant of the fast-moving object, 0.00085. So what does it mean? Using the models described above, I found velocity data for the drops. With no drag, velocity on a dropped object will increase at a constant rate. With drag, velocity increases, but is opposed by drag, and the acceleration is therefore not constant. The fast-falling object reaches 116 meters per second, while the slow-moving object only reaches a speed of 4.45 meters per second. This is because the force of drag begins to negate the force of gravity until the net force on the system is zero and velocity becomes constant. As you can see, this constant terminal velocity of 5.45 meters per second has been reached in the slow-moving object only. So what if the objects were thrown down? I accomplished this by adding an additional downward force to the initial conditions of the slow object models. If you watch the model run, you will see that the gravity force, the downward force, is very large, but the drag force also grows to be very large in effect. With no drag, the object begins to go extremely fast, and with no opposing force, continues to accelerate due to the force of gravity. With an initial force and drag, the slow-moving object is modeled to first go extremely fast, but drag also increases to once again be an equal opposing force, and the object reaches a terminal velocity once again.